All right, let's talk about implicit differentiation. We went over this just a little bit in class, both of the last 2 days, so hopefully not too bad. So I've included a couple of examples. First of all, the basic concepts are these equations generally are more complex and they involve some terms of y, something other than a simple y equals. In the case of the first one, x cubed plus y squared equals y literally has y on both sides of the equation. So what do we do with it? The steps, these 3 steps, are basically the same anytime we try to attack um, implicit differentiation. So first of all, we take the derivative with respect to x. Any x values, we work power rule, same as we have since we started power rule. Anything that is not a simple x value, and this is kind of a result of the chain rule, anything that's not a simple x value, just we have to attach dy dx on the end. So the derivative of y squared is 2y, but since y was not a simple x, we attach its derivative, dy dx. Same thing here. The derivative of y is 1, but since it's not a simple x, we attach dy dx. Second step is we push all the dy dx's terms to one side of the equation, and if we needed to push other terms to the other side of the equation, basically we isolate the dy dx terms, we cut them to one side, and then we factor out. Once we factor out, same as we have Gauss-Cinch algebra 1, we divide both sides by the coefficient of dy dx. So in this particular case, dy dx is equal to 3x squared over 1 minus 2y. Chances are in here, if we wanted to, we might say something about the effect that y can't equal 1/2. That would be a constraint on this particular problem. You put in y can't equal 1/2 because it would cause division by 0, and that's an issue anywhere we go. So how about an application problem at this point in time? We've worked with the unit circle before. Obviously, this comes up in pre-calculus when we're working with our first introduction to sine and cosine. So I decided to work with the unit circle. We've got this equation, x squared plus y squared is equal to 1. So if we're supposed to find the tangent line at the x value of 1/2, first thing we do is we plug in x is equal to 1/2 into the original equation. So we replace x with a half, and then we solve for y. We find out that y is equal to the square root of 3/4, which is the same thing as rad 3 over 2. So we can actually plug that in. Shouldn't be a surprise from you. We know here that the sine and cosine values here of this particular bit, 1/2 and rad 3 over 2, go together. Okay. Now we have to find dy dx just like we did last time. We take the derivative of both sides. Derivative of x squared is 2x. And the derivative of y squared is 2y, but since it's not a simple x, we multiply by dy dx. The derivative of 1 is 0 and always will be. All right? So we push all the dy dx's to one side. We subtract the 2x from both sides. Dy dx is equal to negative 2x over 2y, or clean it up, negative x over y. So now we plug in both the x and the y terms. So 1/2 goes in for the x. Negative x becomes negative 1/2, and rad 3 over 2 goes in for the y. We invert and multiply. The 2's cancel out. We're left with negative 1 over rad 3. Well, negative 1 over rad 3, most mathematicians are going to multiply both the numerator and the denominator here by rad 3 over rad 3. So negative 1 becomes just negative rad 3, and rad 3 in the bottom in the denominator become just 3. So these two things are synonymous here, just rationalizing the denominator, it's called. So we put it in point slope form. Y minus the y value, rad 3 over 2, equals slope that we just found by plugging it into the result of the differentiated equation. We used the derivative, plugged it into the derivative, and x minus the x value, and same as we've been doing. So that's good to start us off with implicit differentiation, and good for the day. Thanks.